Okay, what I want to do is we're going to start by discussing concepts of covalent bonding in the shapes of molecules. Some of the concepts we're going to need to master when we get into other parts of organic chemistry. Okay. Well, first of all, organic chemistry is the study of the compounds that contain carbon. Now, carbon can form chemical bonds in many, many different ways, and that results in over 10 million organic compounds that have been identified. And of course, many more are being discovered every day. The carbon has, like I said, it has versatility in its bonding. It could form triple, double, and triple bonds. It has an intermediate electronegativity somewhere between fluorine, which is very electronegative, and the alkali earth metals. And it forms really strong covalent bonds with other nonmetals, including other carbon atoms, hydrogen atoms, oxygen atoms, nitrogen atoms, and sulfur. We can think of, when we think of versatility with carbon as carbon atoms and their bonding scheme, we can think of something like coal or graphite versus diamonds. And you know how, like diamonds, how aesthetically pleasing they look, and how they're very hard. You know, they're very strong material. Where versus graphite, which is very, very soft. But they both contain carbon atoms. It's just that the carbon atoms are arranged in a different manner in these two types of compound, these two forms of carbon. Carbon can also form bonds between hydrogen, oxygen, nitrogen, sulfur, and it can even form bonds between some metals. So there's a class of compounds called organometallics. So not only does carbon form bonds with other nonmetals, it also forms bonds with metals. Okay, so we're going to do a little bit of a review here. This shows the schematic of the electronic structure of the atom. Remember, an atom is the fundamental constituent of an element, or for that matter, compounds too. It's the fundamental unit of a substance, okay? And there's a one-to-one for elements, there's a one-to-one correspondence between that element and the atom type for that element. So in terms of size, we can characterize the atom. It's on the order of the whole atom itself is on the order of about 1 angstrom, or 10 to the minus 10 meters. Now, if you remember, there was a famous experiment called Rutherford's gold foil experiment, and in that experiment, it was discovered that the atom contains, most of the mass of the atom is concentrated into this really small region, okay, which is 10 to the minus 14 to 10 to the minus 15 meter, and it contains this region here, this small dense region, is called the nucleus. Okay, and the nucleus is composed of two subparticles called protons, which are represented here in blue, and neutrons in green. So the proton is about 2,000. The proton and neutron are about equal in mass, but both of them are about 2,000 times the mass of the electron, but they occupy this really small region, okay? Maybe 10,000 times smaller than the space occupied by the electrons. So actually most of the volume of the atom, or the space of the atom, is actually the electron cloud. So now the electrons are negatively charged, okay, and they surround the nucleus, and they're found in specific regions called orbits, okay, and so again, most of the mass of the atoms in the nucleus and most of the space occupied by the atom is in the electron cloud, or the electron orbits. Okay, so we're going to talk a little bit about electronic structure. It is the arrangement of the behavior of electrons that actually underlie chemistry. Okay, so it's the sharing of electrons between different atoms, or the transfer of electrons between different atoms. Okay, so atoms are confined to regions of space or certain energy levels called principal energy levels. And each energy level can hold up to 2n² electrons, and the different energy levels are n equal 1, 2, 3, 4, 5, and 6, and 7. You can go up in energy level for some of the, theoretically you can go up, but in the periodic table, there's really, the elements are listed in the periodic to the heavier ones. The heaviest ones go up to n equals 7. Okay, so there is somewhat of a correspondence between, there is a correlation between the principal energy level given here and the rows of elements in the periodic table. Okay, so the most important thing in for this slide is that each shell, or each principal energy level, can hold a maximum number of electrons. The other important point is that electrons in the lower energy levels, or the n equals 1 level, well, I should say the electrons in the n equals 1 level have a lower energy than, say, the n equal 2 level, and the n equal 2 level has lower energy than the n equal 3 level. And not only that, but the electrons in the n equal 1 level are closer to the nucleus than those electrons and in the higher energy levels. Okay, so it is this energy, the energy of this electron, which the electrostatic interaction, the electrostatic force between the nucleus and the electrons circling in these orbitals, okay, that holds the atom together. The atom has a certain speed, or kinetic energy, so the electrons would just fly off if there wasn't an attraction to the nucleus. So obviously the attraction for an electron in the n equals 1 level is greater than an electron equal to the n equal 2 level. Okay, so an electron can be ejected from these higher energy levels more readily than it takes more energy to eject an electron from a lower energy level than one of these higher energy levels. Okay, now these main energy levels are actually contain subshells, and these are called orbitals, and the orbitals are designated by the letter S, P, and D. Okay, so now each shell contains a certain number of s orbitals, a certain number of p orbitals, a certain number of d orbitals, and we can go f orbitals too. In this course, we're going to only be dealing with s and p orbitals. The d orbitals and the f orbitals, those are more important for transition, when you study the transition metals or inorganic chemistry, transition metal chemistry. So it turns out that in the lowest energy level, you can only have this s orbital. Okay, and so there's one s orbital in each main energy level. when beyond the n equal 1 level, the n equal 1 level can only have s orbitals. And the s orbital can hold up to only 2 electrons. Now, as you go to the n equal 2 level, or the second highest main energy level, you find that there's two types of orbitals. There's the s orbital, and then there's a new type of orbital called the p orbital. Okay, so the second energy level contains s and p orbitals. Okay, the third main energy level contains a third type of orbital or subshell, and those are called d orbitals. So the third main energy level also contains s. It also contains p, but now you're adding d orbitals. And then in the fourth main energy level, what you're doing is you still have s orbitals, and you still have p orbitals, and you still have d orbitals, but now you're adding this new subtype of orbitals called f orbitals. And it turns out that you can hold only a maximum number of electrons in each type of in the orbitals. Okay, so s orbitals can contain up to a maximum of 2 electrons. The p orbitals, you can put electrons in p orbitals, but you can't put more than 6. Okay, and then in the d orbitals, you can put up to 10 electrons, but you can't put more than that. The f orbitals, you can put up to 14, a maximum of 14 electrons. Okay, and then it turns out to be even more interesting that each subshell beyond the s orbital only contains one type of s orbital, but in p orbitals you can have 3 different types of p orbitals. For d orbitals, you have 5 different types of d orbitals, and then for f orbitals, you have 7 different types of s orbitals. Okay, and the electrons are added to these energy levels. Okay, so what you do is, as you're going up the periodic table, in each element, from one element to another, you're basically adding another proton to the nucleus, because it's the protons, the number of protons, which determine the identity of the element. But what you're also doing is you're adding the electron, and you're adding the electron. The order of filling of the electron is in the order of the filling of these energy levels. So the 1s orbital, there's a single s orbital in the n equals 1 level. So you add electrons to that first, and then you start adding electrons to the second main energy level. An s orbital is lower energy than a p orbital, so you add your electrons to the 2s orbital, and then you start adding them to the 2p orbital. And when the 2p orbital is filled up, you add electrons to the 3s orbitals, and when those are filled up, the 3p orbitals, and then the 3d orbitals. Okay, and again, you can add up to 2 electrons in these s orbitals, up to 6 electrons in these p orbitals, and of course 2s electrons again, a maximum in these 3s orbitals, 6 electrons in these 3p orbitals, and then up to 10 electrons in these 3d orbitals. Okay, so this is called the building up of electrons, or the addition of electrons as you go up the periodic table. Is called the Aufbau principle. So the filling of electrons into these orbitals, suborbitals, and different types of these suborbitals is what determines what's called the electron configuration for that element. The other fact that's important for electron configuration is in one orbital, each type of orbital can hold up to 2 electrons, but the electrons have to be spin paired. Okay, so the electron, because it's a charge, it generates a type of magnetic field or spin. And these spins are either aligned or opposite a magnetic field. Okay, so in an orbital, okay, we can do is we can designate these oppositely paired spins by these half arrows. So the electron in this orbital, one electron has an up spin, and then we say when this electron has an up spin, and then this electron has a down spin, okay, or it's oppositely, the spin is opposite of the other electron in that same orbital. So when two electrons occupy a single orbital, that is called, they have to be opposite spins. That's called the Pauli exclusion principle. So for example, well, we'll get to this, but so if you have the maximum of 2 electrons in this 2s orbital, the 2 electrons have to be spin paired. Now remember I said that the p orbitals contain 3 different subtypes of p orbitals, which we'll get into. So the electron you can only hold up to 2 electrons in these sub p orbitals, and the electrons in each of these sub p orbitals have to be spin paired. Okay, so here's the electronic configurations for the first 18 elements. So the simplest element is hydrogen, which has 1 electron. So that single electron occupies the energy level 1. It's in an s orbital or an s sublevel, and because there's 1 electron, we put the little 1 superscript. Okay. Then we haven't filled that single orbital yet. We can put the second spin paired electron into that orbital. So we add another electron, and we get the electronic configuration of helium, which is 1s2. So these 2 elements, there's a correspondence between the electron configuration and the rows of the periodic table, or the periods. So now if we skip down to a lithium, which is we add another proton to the nucleus of helium, we get the element with atomic number 3, and that's lithium. Now remember that if we have an atom of a neutral element, the number of electrons we add has to be equal to the number of protons for a neutral element, okay? Because the sum of plus charges and the sum of minus charges is equal to 0. So we still keep the 2, we're not doing anything with the 2 electrons we've already added from the first energy level, but now, now what we're doing is we're putting an electron into the 2s level. And there's a typo here. There should be a 2s1. So these orbitals are designated by number 1, which the electron, you know, what orbital or an electron is in, or what sublevel. You have to put an integer that corresponds to the main energy level. You have to put the suborbital type, and then you have to put in. Then what you have to do is you have to put in the number of electrons in that orbital or that sublevel. Okay, so we have 2s2, 1s2, 2s1. So what we could also do is usually what you do, the electrons in the highest energy level that correspond to the 2. So the n = 2 level is the highest energy level for a lithium atom. So what we can do is the electrons in the sublevels that are already filled up, we can represent them by the noble gas in the period above, you know, 1 period above the energy level that we're at on the periodic table, and that corresponds to the configuration. So 1s2, we can designate that as a helium electron configuration. So we put in brackets with the symbol for the noble gas, and then we add the valence electron terms. That would be 2s1. So we keep building up, and until we get to say beryllium. We can hold up to 2 electrons in the 2s orbital, so we can add a second electron to the 2s orbital, and we get the electronic configuration for beryllium. Now, though, what we can only hold a maximum, there's only one type of 2s orbital, so we have to, we've held all the we put in all the electrons in that orbital. You cannot put more than 2 electrons in a single orbital, and they have to have opposite spins, of course. So now what we do is we start filling in. We have to fill in, go up, and we have to fill in the 2 p orbitals. So what we do in this case, now we put an electron into one of the 2 p orbitals. Now remember, there's 3 subtypes of p orbitals. These orbitals are aligned, they have the same, p orbitals have the same general shape, but they're aligned differently in the 3-dimensional space of the atom. So we put this, in the direct, the axis, what is x and what is y, and z is arbitrary, at least for the first electron. So if we assign the first p orbital that we're putting the electron in as x, we're putting a single electron in the 2p x orbital, and we can, so now there's 3 valence electrons because there's 3 electrons in this number 2 main energy level, which is the highest level in boron, and this also corresponds to the second period. So we can simplify this by writing the noble. We still have 1s2, so we write an abbreviation for the for helium, the configuration of helium, and then we add the terms for the valence electrons. Carbon is one element to the right of boron. It now has 6 electrons. It still has the 2 electrons in the lower energy level, 1s2. We also we filled in the 2s2 electrons. We fill in we put 1 electron in that px orbital. But now, instead of putting 2 electrons into the same px orbital, we do is we go to the py, one of the second of the third suborbitals, and so we put 1 electron in 2py. So the reason we do that is because if we can actually minimize electrostatic repulsion among the different p suborbital, 2p suborbitals, by spreading the electrons out into the different subtypes of orbitals, because a px orbital is aligned differently than a py orbital. So what you do is you start putting as you add electrons to 2p, you spread them out, so to speak. So you put this, after you put this electron into the 2px orbital, you put this other electron into the 2py orbital, so you have a total of 6 electrons, but there's 4 valence electrons now. And the rule where you put a single electron into the different sublevels, you first fill up this different sublevels first, is called Hund's rule. And not only that, but it turns out that what you do is you put the electrons into these single electrons into these sublevels so that they have the same spin. Okay, and again, that's Hund's rule. So you maximize the spin. Okay, so these have the same. For example, these would number this electron in the 2px orbital and this single electron in the 2px orbital, 2py orbital would have the same spin. Either both would have an up spin or both would have a down spin. Okay, nitrogen, we have we put, instead of putting a second electron into the 2py and 2px, now we use the third subtype of p orbital, the pz orbital. And so that one, we put the one superscript for the one electron in the 2pz orbital. And now nitrogen, atomic number 7, we have a total of 7 electrons. So again, 2 remain in the lowest energy level, and then we have 5 valence electrons now. There's 2 plus 1, 3 plus 1, 2 plus 1 is 3, plus 1 is 4, plus 1 is 5. So there's 5 valence electrons in a nitrogen atom. Now, when we get to oxygen, we remember there's only 3 subtypes of p orbitals, okay? In energy level, any energy level, okay? There's only 3 types of p sublevels, p sub x, p sub y, and p sub z. So we've now put a single electron in each of these orbitals. So now what we do is we go back and we put a second another electron into the px orbital. Okay, so now, but we put it in the px orbital so that it has an opposite spin of the first electron there. Okay, so now oxygen has this configuration here, where one of the p orbitals, the px, has 2 electrons, and those have opposite spins because they're in the same orbital, and they have to satisfy Pauli's exclusion principle. And then we still have a single electron in the py. So now oxygen, if we count the number of electrons, 2 plus 2 is 4, 1 is 5, 1 is 6. So there's 6 valence electrons. There's 6 electrons in the 2p level, and then there's 2 electrons, the 2 electrons corresponding to the helium configuration in the lower energy level, okay? So these, by the way, these electrons in the lower energy levels are called the core electrons, and then the electrons in the highest energy level are called the valence electrons. It's these valence electrons that determine the important role, the chemical reactivity, or what's happened. They determine the chemistry of the atom. Okay, so we can move on to fluorine. We did oxygen. So fluorine now, we put again a second electron into the 2py, and then we get 7. If we count them, we'll get 7 valence electrons. So there's one single valence electron in one of the p orbitals. But if we fill that orbital now, now we filled up all the 2p orbitals. And remember, there's 3 of these px, py, pz. There's 3 of them. We can put 2 electrons in each. So we can only hold a maximum of 8 electrons in the p orbital. Now, so there's 8 valence electrons. There's 8 valence electrons now in neon. Okay, so now this configuration where you have 8 electrons for an atom in the 2p orbital, or in the p orbital, that corresponds to the configuration of noble gases. So because we can't fill up, we can't like add or remove electrons from the p orbitals because they're filled. What this means is that what this translates into is the inertness of these what's called noble gases, because you contain what's called 8 electrons, and that's called an octet of electrons. So what happens is that the atoms of the other elements, they undergo chemical reactions to achieve this noble gas configuration, 2px2, 2py2, 2pz2. And that's called the octet rule. That applies, though, when you're talking about hydrogen, though. Hydrogen needs one more electron to get to the stable configuration of helium, which is another noble gas. So for hydrogen, it's called the rule of 2. Okay, but for the second group and third group elements, it's called the octet rule, or the rule of 8. Now, if we go to the third main energy level, we've now filled in all the electrons corresponding to neon, but now we start filling, we go up to level 3. We filled in all the electrons and all the orbitals in energy level 2. So for example, I won't, let's go to sulfur, okay? So we start putting electrons into the 3s and then the 3p orbitals. The same rules apply. We spread the electrons out into what's called singlets into each one of the 3 orbitals before we start pairing them. But sulfur, since we have 6 valence electrons or 6 electrons in the 3p, what we have to do is put 2 electrons. We have to spin pair 2 electrons in one of the px orbitals, and then what we have to do is we have to leave, add single electrons to the 3y and 3z. But it's kind of awkward when we go to heavier elements. We're going to start writing out longer and longer electron configurations. So what you can do is you can just write the configuration for the lower energy levels is that of the noble gas in the previous energy level. So what we would do is we would write neon, which would include the electron configuration up to the valence, the n equals 3 level. So here we would have neon, and then we would just write the configuration for the valence electrons, which is in level 3 here. Okay, so that's the that kind of is a background into writing the electron configurations. Okay, so let's for this exercise here, we can, what I'm going to do is, for this problem here, I'm going to talk about this in the next video, and we'll do some work on the electronic whiteboard. Okay, so I will see you very soon.